One final example of one of these double integrals, xy over root x squared plus y squared plus 1 dx dy, and the region R, x ranges from 1 to 2, y ranges from 0 to 1. So our integral is going to be from 0 to 1, and then from 1 to 2, xy over square root x squared plus y squared plus 1 dx dy. We're going to have to do a u substitution on this. So let's let u be equal to what's underneath the radical. So that's going to be x squared plus y squared plus 1. Du is going to be 2x dx if we take the derivative with respect to x, which we should because that's the integral or the variable that's first. We don't like the x, we like the dx, we don't like the 2, so we're just going to divide by 2 to get x dx. So now we're going to rewrite the integral. So we're going to have 0 to 1 and then an integral from a to b now, because now we're changing our variables. X dx is going to be replaced by du over 2. Square root of x squared plus y squared plus 1 becomes square root of u, and then what's left over is y dy. To prepare this for integration, we can just factor out the 1/2 as a result of the du halves. And then we can also, instead of square root of u in the denominator, we can make that u to the negative 1/2 power. And then we're left with du dy. Right, so just some algebra there. Haven't done any calculus except for a derivative thus far. We can go ahead and now take the antiderivative of u to the minus 1/2. So that's going to be, we keep the y there, u to the positive 1/2 over 1/2 from a to b. And then we have our dy that's still left over. Some good news, we have a half and a half. They cancel out. And then we can back substitute for our original variable of x. So we have y square root of x squared plus y squared plus 1. That's going to go from 1 to 2, and then we still have the dy. When we substitute 2 in, we get 2 squared plus 1. That's going to be 5. Right? So our new integral is ultimately going to become y. When we substitute the 2 in, that just becomes 2 squared plus 1, which is going to be 5 plus y squared. And when we substitute the 1 in for x, that's going to give us 1 squared, which is 1, plus the 1 that's in there, in the radical, so that's going to be 2 plus y squared dy. At this point, now what we can do is we can go ahead and break this up into two separate integrals. And so the integrals will be 0 to 1, y root 5 plus y squared dy minus integral 0 to 1, y square root 2 plus y squared dy. And now we can do another u substitution. I'm going to do a different variable this time just because we've already exhausted a and b and u in the previous example. And so let's just go ahead and say, let's just use v and w. So let's let v be equal to 5 plus y squared, and let's let w be equal to 2 plus y squared. Now this is not integration by parts. We're just going through and using different variables, and I elected to use v and w. dv is going to be 2y dy. We like y, we like dy, we don't like 2, so du over 2 is y dy. And then over here, we're going to get the exact same thing. W equals 2y dy, and instead of du, we're going to have dw over 2 equals y dy. And now what we can do is we can substitute into the integrals. I'm going to use bounds c to d. Instead of square root of 5 plus y squared, I'm just going to say square root of v. And then we have, instead of y dy, dv over 2. And this should be a v right here. I think I might have accidentally put a u out of habit there. And then minus, let's just say from s to t of square root of w, dw over 2. Right? And we know that these are both going to be v to the 1/2 and w to the 1/2. And we're going to have a 1/2 that we can factor out. So we're going to have 1/2 We're going to add 1, so we're going to get v to the 3 halves over 3 halves c to d minus 1 half w to the 3 halves over 3 halves st. We're going to back substitute in terms of the original variable. In this case, that's y. So we're going to end up with 1 half divided by 3 halves, which turns into a third. So that's going to be 1/3 of the square root of 5 plus y squared cubed. The square root is a result of the 2 in the denominator. The 3 is going to end up being the cube. Okay, so make sure you understand how we translated that back into the square root of 5 plus y squared cubed. And in a similar vein, this is going to become minus 1/3 square root of 2 plus y squared cubed. All of that ranges from 0 to 1. And now we're just going to apply our fundamental theorem of calculus. We're going to substitute 0 first, then we're going to substitute 1. I'm going to factor out the 1/3 just to make it nice. So when I substitute 1 back in, we get the square root of 5 plus 1 squared, which is going to be 6 cubed, minus 2 plus 1 squared, which is going to end up being 3 cubed, and then minus 1/3. Now we're going to substitute 0 in, so that's going to be square root of 5 cubed minus square root of 2 cubed. Right? And if you wanted to leave the solution that way, that's perfectly fine. Another way to write this is if we distribute the negative, factor out the 1/3, and then simplify all of the radicals. Because remember, we can write 6 to the 3rd as 6 squared times 6, or 6 roots of 6 would be another way. And we could do that in succession with all of the other radical expressions. We could finally rewrite this as 1/3 of the quantity of 6 roots of 6 minus 3 roots of 3 minus 5 roots of 5 plus 2 roots of 2. Notice that we have a negative and a negative that turns into a positive. Right? And I think that's about as simple as we can make this. I'm sure we could factor something else out if we really wanted to, but at this point it's pretty ugly, so we're going to stop at this point. Alright, so hopefully that gives you a good idea as to how to get the exact values for a double integral. In the next video, what we're going to do is we're going to go back and we're going to take a look at the idea of the midpoint rule, and that's going to tell us exactly how the volume type of problem is going to work with respect to double integrals.